Okay, so it's time for the third respiratory challenge. So again, same objectives as the previous two, and which will also be the same objective for the next one. This time, we've got increased pulmonary flow leads to a decrease in diffusion time. The mission, protect arterial oxygen. So the first thing is we need to understand what transit time is. So transit time has to play with diffusion. And remember, diffusion doesn't happen instantaneously. It takes time. Not a lot of time, but it still takes time. And when it comes to diffusion, it's affected by several things. The solubility, which is just dependent on the gas, and so it's different for every gas. Oxygen actually diffuses a little slower or has a more difficult time than carbon dioxide. The thickness of the membrane that it's got across the gradient between the high concentration and the low concentration, and then the surface area. More surface area means it's easier for diffusion to occur. So transit time is, before I go into this, just to remind you, or to tell you, transit time is how long a red blood cell is in the pulmonary capillary, which essentially means that's the amount of time that a red blood cell has for diffusion to occur. Okay? And so the pulmonary capillaries in a typical human hold approximately 70 milliliters of blood. Cardiac output is 5 liters a minute, so if you go 5 liters per minute, or if you go 70 milliliters divided by 5,000 milliliters, or excuse me, let me back up. If you go 5,000 milliliters per minute, divide that by 60, then you get 83 mils of blood per second. Okay, and so what that means is that a red blood cell will spend a little over 0.8 of a second in a pulmonary capillary. Okay, generally that is plenty of time. It normally takes about 0.4 of a second for equilibration to occur. All right, and we can see that on this graph here, where our alveolar oxygen is at 100, our venous oxygen, so that's the blood cell, or the blood that's coming into the pulmonary capillary, is about 40, so our gradient's at 60. Okay, so you can see here, equilibration occurs right around here, so it takes about 0.4 of a second. Okay, so plenty of time. We've got more than double the time we need. But what happens with exercise? Well, if our pulmonary capillaries remain at 70, cardiac output, we're going to say we get up to 20. That means 330 plus mils of blood are going through the pulmonary system every minute, or every second, actually through the body every second. So that means a red blood cell is only going to spend about 0.2 of a second in a pulmonary capillary. So that means we're right about here. Okay, that's not enough time. Remember, it takes 0.4 of a second for equilibration to occur. That's not great. So how do we account for this? Because during heavy, intense exercise, we're pumping 20 liters of blood, but we need the oxygen to make it worthwhile. And so what happens is we have recruitment and distension. Okay, and so if you look at this picture here, there's two things that are going on. This is us right here kind of normally. Notice that, just think of kind of this space as capillaries and alveoli. Okay, we're not using all of our alveoli at rest. We talked about this earlier with AADO2. So an example of this would be at the top of the lung. We've got airflow, but we don't necessarily have the best blood flow. All right, and so what we can do, because of the increased pressure, we actually start sending blood to those capillaries that aren't being used under resting conditions. So we're recruiting more capillaries. The other thing that can happen is we can actually cause these capillaries to get a little bit bigger. Okay, so notice that we go from this width to the other width. I don't have any way to measure that or show you that we've gone from 1 millimeter or whatever to 5 millimeters, but we can distend, or they can get bigger. All right, they're not going to distend a lot, but they can distend a little bit, which will help allow for more blood to come into the pulmonary capillaries. So what happens is our pulmonary capillaries can increase their blood volume by about 3 times. So we go from 70 up to 210. We take that cardiac output that's 20 liters a minute. That gets us to 333 mils per second, like we were talking about. And so now our red blood cell is spending 0.6 of a second in the pulmonary capillary. And this 0.6 of a second here, and then the 0.8 that we were talking about earlier, that's our transit time. And since 0.63 is greater than 0.4, we still have lots and lots of time to equilibrate. But what happens if we're in hypoxia? Well, it says wait until November. I forgot to update the slide, so wait until April. Okay, so we will talk about this in a couple months. So April. Sorry. All right, so there are going to be times, though, where this still isn't enough. Transit time won't be big enough. Okay, eventually it is possible in some people that the pulmonary system can't increase its volume enough to accommodate this increased flow due to increased cardiac output. Okay, and so that's what this figure is trying to show here, is that the blue line is transit time, the red line is pulmonary capillary blood volume, and then the black line is arterial oxygen. There comes a point here where transit time's decreased enough and capillary blood volume is essentially tapped out, that at this point here, transit time has dropped so much that we can't have complete equilibration, and so arterial oxygen starts to decrease. And so we go from being a perfusion limited person to a diffusion limited person. Okay, if we're perfusion limited, that generally means that we are not getting enough blood flow to pick up oxygen. Most of us in this room, or I talk as if we're all here, but most of us in this class, probably all of us in this class, our VO2 max is going to be limited by the cardiovascular system. Okay, but in elite athletes especially, that limitation can actually be a respiratory system thing. Okay, because their cardiac output can get high enough that their lungs can't accommodate or diffuse enough oxygen in to take advantage of that. And the reason why isn't because they're not breathing enough, they're breathing more than enough, but they don't have enough surface area in their lungs to have this oxygen diffuse out of the alveoli and into the bloodstream. Okay, and so what can happen is we have something called exercise-induced hypoxemia. And in this case, ventilation is not able to keep up. And really what it is that we're not able to diffuse oxygen out of the bloodstream into out of the alveoli into the bloodstream. Okay, again, ventilation is plenty high. We've got enough oxygen, we just can't get it into, we don't have enough surface area in our alveoli and the pulmonary capillaries to get it into the bloodstream. Okay, and so there's a couple of reasons why this can also happen. So we can have VQ mismatch, we can have shunting. So at high intensity exercise, we might have a lot of those intrapulmonary shunts. We might be having more blood flow through a PFO if that occurs. And really, this is probably the main one, is that we're not equilibrating. Our transit time isn't high enough for complete equilibration to occur. And so that is challenge number 3.